Somebody asked me if these graphs that I came up with to explain the expansion of the universe can be modeled using simple functions. And the answer is yes, but we have so very little data, we know so very little actual data about this function that those models are just kind of meaningless. But it is an interesting exercise to try to come up with functions that match these behaviors of derivatives. So let's do that. Let's first talk about the units of the function I'm trying to model. U is supposed to represent the size of the universe over time. So the x-axis will be time measured in billions of years. Right now, it's supposed to be 13.8 billion years after the Big Bang, which I'm going to put at the origin of coordinates. The y-axis is going to be the average distance between galaxies in the universe, which right now has been measured to be about 1 million light years. So it's going to be measured in millions of light years. So this point here is 13.8, 1. Before Hubble, people thought the universe was static. It was always the same size, so there would be always the same average distance between galaxies. So the model would have been a constant function equal to 1. And then came Hubble in the 1920s and showed that the universe is actually expanding. So a simple function that could fit this data would be just a linear function that goes through the origin and is increasing up to 13.8, 1. And it's easy to come up with the equation of such a line. Now, in the 1990s, scientists claimed that the universe is actually expanding right now at an accelerated rate, that the second derivative is positive. And well, to model something like this, we're going to need at least a cubic function, and a cubic polynomial does the job. For example, using this cubic function, it goes through the Big Bang at the origin. At 13.8, the value is 1, and then the expansion accelerates. In 2024, a team claimed that, in fact, even though the second derivative is positive, the universe is accelerating in its expansion, the third derivative is negative, so the acceleration is decreasing over time. And to model something like this, we're going to need at least a quartic function, and I can find quartic polynomials that do the job. For example, this quartic polynomial satisfies all the characteristics we want. It goes through the origin, so through the Big Bang. At 13.8, the average distance between galaxies is 1. The acceleration of the universe is positive at this moment, but then the acceleration starts to slow down. And in this particular model, it predicts that it slows down so much that the universe starts contracting and it ends up in a big crunch. And now the latest news is that the physicists think that the universe's expansion may be already slowing down, that the second derivative may be negative and it is increasing, but at a smaller rate. And at some point, it may start decreasing in size. And to model that phenomenon from a big bang to a big crunch, we can simply use a parabola. This is simple enough to model using a quadratic polynomial with a parabola for a graph that goes through the origin. So through the Big Bang, at 13.8 is 1, but the expansion is already decreasing because the second derivative is negative, and therefore it will reach a maximum size or a maximum average distance between galaxies before it starts to contract and ends up in a big crunch.